Another type of graph in graph theory is the idea of something called a complete graph. And we define a complete graph, K sub n, is essentially a simple graph in where all the vertices are connected by exactly one edge. All right, so for instance, if we had 3 as K sub 3, and we'll see that in a moment, we would basically say that we can do a traversal. In other words, we can move from any one vertex to another vertex in K in any one move. All right, so it shouldn't take us like 2 traversals, so we shouldn't have to hop. We can go from any vertex to another vertex easily. We have this other type called a complete bipartite graph. And we're going to have 2 sets of vertices, V and W, defined as K M sub n. So M and N are both going to be integers. All right. And there's 3 rules for a complete bipartite graph. And they look like there's a lot to them, but really it's pretty easy for us to construct these. So there's an edge so that you can traverse from V to W in one traversal. So basically go from any vertex in V to any vertex in W. But there are no connections immediately from V to any V. All right. So basically V1 is not incident upon or adjacent to V2, and V2 is not adjacent to V3, and V3 is not adjacent to V1. All right. They're only adjacent to all the vertices in W. And similar in W, none of the vertices are adjacent to one another. All right. So with all that said, let's take a look at a few examples of how to construct these complete graphs. All right. It's actually pretty easy. So for letter A, we have K3. So we're going to draw 3 vertices. Right? And this is just one way of doing it. Okay. And we can go from here, here, and then here. All right. So if I call this like A, B, C, and let's call this edge 1, 2, and 3. All right. We can go from any vertex. So we can go for, we can traverse this way to go from A to B. We can go from A to C really easily here, and go from B to C. All right. Now that's not the only way to construct this, right? Another way to construct this would be this, right? All right. And let's say we called this A and this B and this C, and we go from A to B in one traversal, and then B and C are connected here, and then A and C are connected here. These graphs are something called isomorphic, and we're going to take a look at that later in the course with isomorphisms. But just wanted to let you know that there's not just one way to be able to construct these complete graphs. All right. I'll do the same thing for K4 just to show you. And you might want to pause the video and just try to construct K4 on your own. All right. But this is the way I would do it. All right. Or one of the ways. I'm going to show you 2 different ways to be able to construct K4. And I'm not going to label the vertices or edges this time, but we could just do this. Right. So that's one way of constructing K4. Another way, and I don't know which one's more aesthetically pleasing than the other. All right. But we could almost have like a pyramid structure. All right. So both of the, and again, these graphs, if you could label the edge sets and vertex sets, would be isomorphic to one another. Okay, so again, this is the graph of K3, this is the graph of K4. Now, a complete bipartite graph, K23, is actually pretty easy. Okay, so what I'm going to do is I'm just going to have, let's just call this V sub 1, and let's just call this one V sub 2. And again, we're trying to draw K23. So vertex set V has 2 vertices, and vertex set W has 3 vertices. So this, and then this, and then this. All right, so we'll call this like W1, W2, and W3. And this is really easy. All you're going to do is just draw an edge so that V1 is incident to all of the vertices that are in set W. And then you're going to do the exact same thing with V sub 2. All right, so you would get a graph such as that. And notice that you can't traverse from W1 to W2. You can't traverse from W1 to W3. You can't traverse from V1 to V2 in a single traversal. All right, it would actually take you multiple traversals, at least 2, to be able to do this. In real life, think of like punching in your ATM card. Okay, so you put your ATM card in, and then what it does is it checks to see whether you put in the right PIN number. And then once you do that, then it spits you back out to the screen to where you can access your funds, right? So that might be like a pretty simplistic example in real life where you might use like complete bipartite graph. Another way to be able to traverse these sorts of graphs is looking at the ideas of paths and circuits. And there's, again, just similar to the introductory video, we have a lot of definitions, all right? And so let's make sure that we're okay with these definitions. So we have a walk. A walk is the most simplistic type of traversal of a graph. Basically, you can move anywhere from a vertex V to a vertex W. So you can go back over the vertices, you can go back over the edges as many times as you want. A closed walk is going to be a walk, so you can move anywhere you want, but it begins and ends on the same vertex. All right, so if you started on vertex 3, you could walk here, 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 and then back. All right, and that would be a closed walk. All right, so notice with a closed walk or any walk, you can repeat edges and vertices. That's not true with a path. A path, just like if you were to try to go through like a path in the woods or something like that, it's a walk with no repeated edges. All right, so it's basically like a line, okay, if you would. So with a path, you couldn't do this. All right, so that's not a path where you go back over any vertex. All right, a simple path is a path with no repeated vertices. All right, so it is possible to go through a path but repeat some of the vertices. So for instance, like if you look at vertex 5, all right, we could do something like this for a path. We could go here, 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 and notice you could repeat, all right? But in a simple path, that's not the case, all right? So, and then finally, we have a circuit, which basically is a closed walk, all right? Remember, a closed walk begins and ends on the same vertex, but it does not have any repeated edges. And then a simple circuit is the most constricting of all of the types. It's a circuit, so closed walk, no repeated edges, but also no repeated vertices except the first and the last. All right, so simple circuit is going to be the toughest one for us if we're ever asked to do that. But let's just go through and try to answer these three or try to respond to these three. All right, so for letter A, we want to find a path from 1 to 4. All right, and there's a lot of them, right? So one way to do this, and when we do this, we're gonna write it in this fashion. So we're gonna start at 1, and we're gonna select V6. All right, so we're just going from here to 5. All right, and notice when we do this, we have a vertex, we have an edge, a vertex, and then another edge. Let's just make V3. And then finally, the vertex that we're ending with. Okay, so when we label these, we want to make sure that we label both the vertices as well as the edges, just in case we have parallel edges. All right, we want to make sure that whoever's looking at this knows specifically which of the different traversals we used. Right? For letter B, it asks us to find 3 walks from 1 to 2. All right, that's pretty easy. So one walk would be 1, V1, and 2. Really easy. Another one would be 1, V6, 5, V2, 2. And then finally, a third one from 1 to 2 could be 1, V5, 3, V7, 5, V2, 2. Right? So in other words, we could go this way, here, here, here to 2. All right. So that might be a way that you guys can think of your walks. And remember, walk is the least, has the least restrictions of any of the different types of traversals. 2 circuits from 1 to 1. Right? Remember, a circuit begins and ends on the same vertex, but also it's a closed walk. All right, so that means we have to end up at the same place that we started with. So for letter C, so 1 is just going to be this, right? That's a pretty easy one right here. So we have 1, V6, 5, V2, 2, V1, 1. All right, but that's not the only circuit that we have. All right, another one could just be around the perimeter, right? So we go, or we can just even do this. Okay, so that would be another one. That's probably like one of the most simple ones we did say. So 1, V5, 3, V7, 5, V2, 2, V1, 1. All right. So hopefully you can see that these sorts of things are not too difficult to be able to maneuver or traverse. All right. So this is some of the more elementary stuff with graph theory. All right. And so in the next video, we're going to start taking a look at the idea of some isomorphisms, all right, which are generally a little bit tougher. And then we're going to finish out by looking at trees.